Okay, so in the last lecture, we have seen how we can use first order and second order derivative filters to find out the high frequency components and detect the edges or isolated pixels, right? So now we'll see one specific type of second order derivative filter for image enhancement. So these filters are isotropic filters, okay, which are rotation invariant. Means in this the filtering is independent of the direction of the image. Okay, so rotating the image and then applying the filter gives the same result as applying the filter first and then rotating the image. Okay, the result will be same. So Laplacian is a second order derivative filter and the function is given here as this. Okay, so what we are doing is we are going to find out the second order derivative in x direction and second order derivative in y direction. Now you know what is second order derivative in image with respect to image. That is uh, f of, it's a difference, right? We have seen last lecture, f of x plus 1 plus f of x minus 1 minus 2 of fx, that we have seen. So the discrete version in x direction of second order derivative is given by this formula. This we have seen last lecture. In y direction is this. So you can just substitute these two things in this function. Okay. So after substituting, we'll get this. So this equation can be implemented by a mask. So here you can see this mask. Okay, so we have only four neighbors. Here we are considering only four neighbors. Okay, if you check the sum of all the coefficients here is equal to 0. So I told you before also the sum of all the coefficients of high pass filter mask should be always 0. And this is another mask. What is the difference between this and this? Here the sign is reverse. Okay, so but sum of all the coefficients is 0 only. Okay, so here in this filter, in this filter mask, we are using all the neighbors, diagonal as well as vertical and horizontal. And similarly this just reversing the sign order. Again the sum of all the coefficient is equal to 0 here. So what is Laplacian? Laplacian is a derivative operator, and this we have already studied in last lecture. It's a second order derivative operator, and its uses highlights the gray level discontinuities in an image and de-emphasizes regions with slowly varying gray levels. So what is the meaning of this? If this is the image having this object, what will happen if you apply a Laplacian? You will get only the edges. Okay, you will get only the edges. Here we'll get the response only at the edge, and remaining everything will be black. Remaining everything will be black. Okay, why this is happening? Because the filter give response only to the edges, only for a high frequency. Okay, so edges as well as isolated pixels, the frequency is high, so filter will give response only for that, and remaining everything will be 0. Okay, so that's why it is written here. It produces the image that have grayish edge lines and other discontinuities, all superimposed on a dark featureless background. So the entire background will be black, and only at the edges you will get the response. Okay, so background features can be recovered. Now what we are expecting, what the user is expecting, if user has this original image, okay, this is the original image, you can have original image. Okay, after applying high pass filter, I am getting a black featureless background with the edge, only edges. Okay, only edges I'm getting. But what I am expecting, I expect that I should get the original image plus sharpen edges, okay, but I am getting right now only this. So what I have to do is I have to add the original image to high pass filtered image, okay, then only we'll get the sharp image, right? So when I just talk about high pass filtered image, I'm getting only the edges, okay? But if you add to the original, you will get original image plus sharpen edges. Okay, so this is what is written here. Background features can be recovered while still preserving sharpening effect of the Laplacian operation simply by adding the original image to the Laplacian image. So now you know what is this. This is your original image and this is your Laplacian mask, okay, Laplacian filtered image. So why there are two equations? Because if you remember in the previous slide we have seen for the Laplacian mask, one mask was like this, -1 -1 -1 -1 plus 4, and another mask was -4 plus 1 plus 1 plus 1 plus 1. That's why there are two equations, okay. So now you have to just add this f of xy in the previous expression and you will get this. Okay, so I can represent this using a mask. Now what is this? F of x plus 1, f of x. So you will get this pixel 1, 1, 1, 1 here, and this will be 5. Okay. So here you can see this is the original image, okay. Then this is a Laplacian filtered image with black featureless background. Only at the edges we are getting good response. Then they have used some histogram or some scaling operation, and then they have added this to the original image. So here you can see the difference. This original image, okay, this was the original image, and this you are added in this, so you got original image with sharpen edge. So this is the mask which I told you. After adding f of xy, you will get at the center you will get 5 here, okay. So here if you see, if you apply the sum of all coefficient is not equal to 0. Why? Because you are adding the original image to the sharpen image. Okay. Similarly, this is the version of the next. The second mask was, it was 8 in at the center, right? So if you add f of xy to that, you will get 9 here. Okay, next we'll see. So we have seen till now we have seen ideal high pass filter and Laplacian filter. Okay, next is high boost filtering. So unsharp masking. So what we do here is this is a sharpen image and this is original image minus blurred version of the original. Okay, so can I say that the high pass filtered image is equal to original minus low pass filtered image. This we have seen in that formula, in that problem also. In the problem you have solved original image equal to high pass filtered image plus low pass filtered image. Okay. So the process of sharpening the image consists of subtracting a blurred version of the image from the image itself. So generalization of unsharp masking is called high boost filtering. Okay. So high pass filter, this is just now I told you high pass filtered image equal to original minus low pass filtered image. So it is represented by HB. What is HB? It's a high boost filtering. Okay. So f of HB xy is equal to a of f of xy minus blurred version of f of xy, and a is greater than equal to 1. Okay, so can we rewrite this as this? We are just adding and subtracting f of xy from this. Okay, we are adding f of xy and subtracting f of xy, so I will get this. Okay, so a is an amplification factor. So f of fs can be obtained by the equation this. Okay, a of f of xy minus Laplacian f a into f of xy plus Laplacian. A is a amplification factor. So what will happen if a is equal to 1? If a is equal to 1, it's the standard Laplacian, right? A is equal to 1 means standard Laplacian. And if A here, if A is equal to 1, okay, you will get standard Laplacian. Okay, if A is greater than 1, then Haber-Bosch image looks like more like original image multiplied by a constant. So it is, we are boosting the values, so that's why it is called as Haber-Bosch filtering. So when the original image is darker than desired, by varying the boost coefficient, it is possible to obtain an overall increase in the average gray level of the image. You are increasing the brightness. Okay, that's why it is called as an overall increase in the average gray level of the image. So here for different values of A, the images are shown. This is the original image. Okay, for A equal to 0, you will get this. A equal to 1 and A equal to 1.7. Now next is first order derivative filter, that is known as gradient filter. Okay, what is the meaning of gradient? Gradient is slope, right, or derivative. So the function f of xy, the gradient, okay, of f at xy is defined as 2D column vector. So now this is a gradient, and gradient in x direction and gradient in y direction. So gradient in x direction is given by this, and df by dy is a gradient in y direction. Okay, the magnitude of this vector is given by square root of gx square plus gy square, and you can just substitute this here. Okay, you will get a magnitude. Similarly, you will get a phase angle also. Okay, so partial derivatives are not rotational invariant. Okay, its magnitude is rotation invariant. And for simplicity, we can say that this gradient is equal to mod of gx plus mod of gy. These are the different masks which are used for gradient filter. So here you can see these are known as Robert mask. Okay. Similarly, these two are Sobel operators. These are Robert cross gradient operators. So if I want to find out, this is if I want to find out the value over here, the formula is given: gx is equal to z9 minus z5, and gy equal to z8 minus z6. Okay, and this is the gradient which is given. So at z5, the magnitude can be approximated by this formula: z5 minus z8, z5 minus z8 plus z5 minus z6. So this is another approach. This is the formula you can just remember, and this was for Robert. Okay, so Sobel operators which are shown in the previous slides, you have to just apply this formula to find out the gradient. So the difference between the first and third row 3 by 3 image approximates the derivative in the x direction. What is the meaning of this? So this is your image, the difference between the first row and second row. Okay, it approximates the derivative in the x direction, that you know, right? So this, if the difference is in this direction, then it's a x direction difference, right? And the difference between third column and the first column, the difference between the third and first column approximates the derivative in the y direction. So in the mass shown, the sum of all coefficient is equal to 0. It indicates that they will give response of 0 in the area of constant gray level. So this is also a high pass filter only, right? First order derivative. So whatever is applicable to the high pass filter mass, it is applicable here also. The sum of all coefficients is equal to 0. So gradient is used in the industrial inspections to aid humans in the detection of defects, highlight small spaces that are not readily visible in the grayscale image, and enhance the small discontinuities in an otherwise flat gray field. So here one more example. This is the optical image of contact lens, which is shown here, and this is a Sobel gradient. Okay, so while operator is applied on this to get the age. Okay. So one more important. Okay, the one more important thing is suppose this is your image. Okay, and this is the age in the image. Okay. Now I want to find out whether the age exists, whether there is an age or not in the image. Okay, how computer will come to know whether there is a age. Okay, so what we have to do is we have to compute the gradient in all possible directions. Okay, now suppose I am getting the gradient. Okay, the gradient in this direction. What is the meaning of gradient in image? It's a difference, right? So it's a difference. So if I am getting more difference in this vertical direction, means the edge exists in horizontal direction. Okay. Suppose the edge is vertical. Okay. So uh, the difference will be in more in which direction? The difference here will be difference in gray level values. Okay, will be more in which direction? It will be in horizontal direction. So when the difference is more, the gradient exists in one direction, the edge will be perpendicular to that direction. Okay, I'll give you one example. Like suppose this is your image. Okay, so what can you say about this? The difference is more in which direction? The difference is more in x direction, means the edge exists in y direction. Yes or no? Okay. Similarly, suppose this is your image. And you have this. So the difference is more where? Here. So edge exists in this direction. Okay. So this is how we are going to use the gradient operator to find out the edge. So this is one more example shown here. The whole body scan. This is a Laplacian which they have applied, and after that they have added the original with Laplacian, and they got this image. This is the original plus sharpen edges. So that's it for this lecture today.